Section 2.4, Continuity. The simplest definition of a continuous function is that you can trace the graph without lifting your pencil from the page. In this section, we're going to use limits to formally define continuous functions. We are looking at three different graphs. Each one of these graphs are not continuous, meaning they fail the continuity test. And they each fail in a different way. In the first graph on the left, we see that there's a point missing along this line. And that's representing the fact that the function is not defined for the input x equals a. So if we try to plug a into our function, it is undefined, therefore we have a missing point on the line. In the middle graph, this function is not continuous. If we tried to trace the graph with our pencil, we would have to pick it up, and then we could place it back down on the second half of the graph. We can tell that this function is not continuous because there's a gap right here. And then all the way on to the right, we have the same scenario as the first picture, but in this case, the function is not undefined. If I plug a into my function, I know to go up to this solid dot. The problem is that solid dot is not the same value as what the limit of the function is approaching as x is approaching a. So these three conditions are what we use to define continuous functions at a point. So we'll first start by looking at specific points on a function, determining if the function is continuous at that point, which means we need to check three conditions. One, the function has to be defined at that point. Two, the limit needs to exist as the independent variable approaches the x value at that point. And then three, not only does the limit have to exist, like we said in part 2, and not only does the function have to be defined, like we said in part 1, but part 1 and 2 need to be equal to each other. That's what the third condition is saying. So we'll check the function's defined, we'll check that the limit exists, and then we'll check to make sure that those two things are equal to each other. Let's practice determining continuity at a point for the function x squared minus 4 divided by x minus 2. We want to use the definition of continuity to determine whether or not this function is continuous at x equals 2, which means we need to go through and check that all three conditions are met. So let's start with our first condition. Is the function defined at x equals 2? That means if I were to plug 2 into my function, would I get a number to come out, or would I get some nonsense? So let's try it. I'll plug in 2 for x and simplify. In fact, we're getting 0 over 0, which is an indeterminate form. So we're not quite sure if the function is defined just by plugging in x equals 0. What we can do instead is look at the domain of f. Remember that the domain is all the x values that will make that function work. In this case, we can look at the denominator. We see that x minus 2 has the potential of being equal to 0. If that's equal to 0, then our function is undefined. So let's set our denominator equal to 0. We'll solve. The value x equals 2 causes f of x to be undefined. So first condition already not met, which means this function is not continuous at x equals 2. We could go on to check that the other two conditions are met, but all that matters is that one of them failed. One of them failing is enough to say the function is not continuous. So it's not necessary for us to check the other two conditions. If we graph the function, we can see what's going on. At x equals 2, we have an open circle, and that's because the denominator has a 0 when we plug x equal 2 into it. If we wanted to verify that the limit does exist as x approaches 2, we could look at what's happening as we're approaching x equals 2 from both sides. And it looks as if we should be approaching the output. The function is outputting 4. But because the function's not defined there, we already know that we've violated the continuity condition number 1. Let's take a look at another function here. This time we're looking at a piecewise function that's split at the x value 3. If x is smaller than or equal to 3, then we'll use this parabola for the definition. However, if x is larger than or equal to 3, we'll use this line equation for the function. We want to know, is this function continuous at x equals 3? So the first thing we need to check, is the function defined at x equals 3? Well, if I try to plug in 3 to my function, let's see what happens. Based on the definition, I'm using a number that is equal to 3, which means I need to use the top form, the top definition. So if I plug in 3, I have to use that top one. So I'll have negative 3x squared plus 4. That looks like a parabola. I have no issues with this being continuous. This function is defined at negative 5. Sorry, the input of x equals 3 gives us the output of negative 5. So is the function defined? Yes, it is. I'm going to write that shorthand f of 3 equals negative 5. And then we'll move on to the second condition. The second condition says that the two-sided limit of the function has to exist. Now remember, I know it's the two-sided limit because there's no plus or minus following the a in the limit notation. Now because this is a piecewise function and we're approaching the x value that is what splits the definition, we're going to have to do one-sided limits, one at a time. We're going to check the left limit, then we'll check the right limit. And if those two things match, then we know that the two-sided limit exists and is equal to the one-sided limits. To do the left limit for this piecewise function, we have to think about the fact that x is approaching a, which is 3, from the left. And I'll draw a little number line here so that we can remember if we're coming from the left and we're heading towards 3, we're using numbers that are less than 3. So then, in order to stick with the function definition, I need to use the top part of this piecewise for the left limit. And then we can simply evaluate the limit. This is a polynomial, which we know is continuous. We can just do direct substitution. That looks like negative 3 squared plus 4, which we know is equal to negative 5. And then we can move on to the right-sided limit. In this limit, x is approaching 3 from the right. And if we look at our number line, approaching 3 from the right means that we're using x values that are larger than 3. So then we look at our piecewise definition and we say, if x is larger than 3, we'll use the bottom half of this piecewise definition. So when we rewrite our limit, it'll look like this. And then we'll plug in direct substitution and simplify. We calculated the left limit, we calculated the right limit. Now we want to compare their values. The left limit was equal to negative 5, the right limit is equal to positive 4. These are not equal to each other, which means the two-sided limit does not exist. Which means we violated the second condition for continuity. This function is not continuous. Let's take a look at the graph so that we can see what's going on here. In this picture, we can see that we have the downward facing parabola for x values less than 3, including x equals 3. And then the second half of the piecewise starts at x greater than 3, so we have an open circle and then the line that finishes the piecewise function off. We just showed that the second condition failed, meaning the two-sided limit does not exist. And we can see that from the graph. If we were coming from the left, it looks like our limit is approaching -5, I think is what we said. Yeah. And then if we were coming from the right, it looks like we're approaching +4. So we have a huge gap here. The two-sided limit, therefore, cannot exist. This function is not continuous at x equals 3. We're practicing determining continuity at a point. We've seen an example where the condition 1 fails. We've seen an example where the condition 2 fails. An example where the condition 3 fails would just look like a function that is defined, the limit does exist, but the limit is not equal to what the function's defined to be. So let's try another example here. This is another piecewise function. This time the function is defined with that fancy sine x over x, as long as x is not equal to be 0. And if x is 0, then the function output is the point 1. So we have x equals 0, function output is 1. So we want to know, is the function continuous at x equals 0? Condition number 1, what happens if we plug 0 into our function? Well, we just said that. It spits out 1. So yes, first condition is met. Second condition, does the limit exist? Well, in the last section, we spent quite a bit of time showing that the limit as x approaches 0 from both sides for the function sine x over x. This is a very important limit from the last section. We said that that is equal to 1. So we know the second condition is met. The third condition says that what we found in step 1 and what we found in step 2, they have to be equal to each other. So we look at the function definition for step 1, we look at the limit value for step 2, and we see that they are in fact equal, which means the third condition is met. The limit is equal to the function being evaluated at 0. So this function is in fact continuous. And if we wanted to graph it, we could. We've seen this graph before. And if we wanted to trace this graph with our pencil, we could totally do that without ever having to pick up our pencil, even if we do a terrible job at graphing it.